Lesson 10.1, the language of hypothesis testing. The objectives for this lesson is to be able to determine the null and alternative hypothesis, explain type 1 and type 2 errors, and state conclusions to hypothesis tests. So let's recall the inequality symbols that we have learned prior to this. And then let's move on to two types of inferential statistics. The first one is estimation, and this was covered in Chapter 9. Now we're going to move on to hypothesis testing, which is covered in this chapter. So let's look at an example. We have a friend and she flips a coin 5 times and then ends up with all tails. What is the probability of getting all 5 heads? So if you recall, probability of 5 tails. This is the probability to get the first one tail, second tail, third, fourth, and fifth. Because a flip of the coin does not depend on what happened in the prior flip, you can just take the probability of each one of these and multiply it. And the probability of flipping a tail is 0.5 each time. So when you do that, you should get 0.03125. This is less than 0.05, so this would make this unusual. So we have the heart of hypothesis testing. First part is make an assumption about reality. So for example, in our example above, our friend is not cheating. Then collect sample evidence to determine whether it contradicts the assumption. So let's define hypothesis. This is a statement regarding a characteristic of one or more populations. And then why do we test statements about a population parameter using sample data? We do this because it is usually impossible to gain access to the entire population. All right, and then let's just jump into defining hypothesis testing. This is used to test statements regarding a characteristic of one or more populations. Here are the 3 steps in a hypothesis test. First, make a statement regarding the nature of a population. Then collect the evidence, so your sample data, to test this statement. And then analyze the data to assess the plausibility of the statement. Okay, in hypothesis testing, we have a null hypothesis and we have an alternative hypothesis. We will always have both of these. The null hypothesis is denoted as H sub 0. This is a statement to be tested. The null hypothesis is a statement of no change, no effect, or no difference, and is assumed true until evidence indicates otherwise. So when you see this no change, no effect, or no difference, you should be thinking equals. So with the null hypothesis, it's always h sub 0. We're going to have some symbol here. So if we're talking about means, it's always going to be equals for your null. And then alternative hypothesis is denoted as h sub 1, or sometimes it is denoted as h sub a. I believe our book uses the h sub 1, but just so you're aware, it is written like this as well. This is a statement that we are trying to find evidence to support. So there are 3 ways to set up the null and alternative hypothesis. For the two-tailed test, we have your h sub 0, your null hypothesis, and your parameter equaling some value. Your alternative hypothesis is your parameter not equaling some value. So when we have the not equals, that's going to be a two-tailed test. Some keywords would be too little, too much, no difference, different from. A left-tailed test, we have our null hypothesis with our parameter, again equaling some value. And then our alternative hypothesis is our parameter. So parameter is like mu, proportion, standard deviation. It's going to depend on your question. Less than some value. Keywords here are going to be less than, fewer than. And then we have a right tail. So we have our null, again a parameter, is equal to some value. Our alternative hypothesis is our parameter greater than some value. Keywords here are greater than, more than, higher than. Okay, notice again the null hypothesis is always the parameter equaling. This is true for every null hypothesis, so that's nice and easy. The left and right-tailed are considered one-tailed. So let's start with some examples. For each situation, determine the null and alternative hypothesis. State whether the test is two-tailed, left-tailed, or right-tailed. The medical pharmaceutical company has just developed a new antibiotic for children. 2% of children taking competing antibiotics experience headaches as a side effect. A researcher for the Food and Administration wants to know if the percentage of children taking a new antibiotic and experiencing headaches as a side effect is more than 2%. Okay, so it's some keywords. I'm seeing percentage and is more than 2%. So if you remember, the alternative hypothesis is always going to equal something. Now, what are we working with? We're working with percentages. So we can put a P here for proportion. Our alternative, these always have to match up, your parameter. Now, what are we looking for? More than. More than what? 0.02. Once you have this filled in, then you can copy that number up here. So these numbers always need to match. These parameters always need to match. This is always an equal sign. So basically you get this information within the problem to figure out what the letter is, the parameter, what the symbol is, and what the number is. Okay, this is a right-tailed. If you look back at our notes we just did, the Blue Book value of used 3-year-old Chevy Corvette Z06 is $56,130. Grant wonders if the mean price of the used 3-year-old Chevy in the Miami metropolitan area is different from $56,130. So keywords here are mean and different from $56,130. So our parameter we're working with now is the mean. So we're going to write mu. This is always equals. Different from means not equal to. And what number are we working with? 56,130. Because of this not equal to, this is a two-tailed. And the standard deviation of the contents in a 64-ounce bottle of detergent using an old filling machine is 0.23 ounces. The manufacturer wants to know if the new filling machine has less variability. Okay, now we're working with standard deviation. So put that in there, put your equal. Has less, that means less than. And what are we working with? The 0.23 ounces. Okay, because we're concerned about the 0.23 ounces being filled, not the container it's going in, but the amount that's going in to that 64-ounce container.